So good morning to all of, and I welcome all the participants in our third day session. So see, today there is a minor change in the schedule that initially actually the lecture was supposed to be taken by the Professor Ram Vilas Pachori, but since he has some urgent meeting in Bangalore related with his fellowship, that's why he is not able to deliver it today. And probably he has agreed to give his lecture on the Saturday. On 20th, he will give it. That's why, that's the opportunity. So I will continue. In the afternoon part, the lecture will be taken by Dr. Himanshu Padule regarding some medical images, etc. Medical is one of the application of these image processing that you will see from the 3 to 5 lecture. So regarding yesterday's lecture, since no more question was there hardly, and I had the feeling that it was not well understood. So just I am going through it because I felt it later that it was not covered properly. So that way, so what we would do that first. Yesterday's content, actually these contents are all basics. How the things are basically done in the image processing. How, because once you understand the basic things, then you are able to replicate those things with your own idea. That's why these things are a bit important to understand. So instead of before going to the new content, I'm going through it again so that uh, I can be very well assured that it has been delivered to all. Are you with me? Am I audible? Thank you, Jyoti. And please feel free. Thank you, Shilpa Saraswati. Please feel free wherever you feel any type of doubt. Even I may not able to, it may happen that I may not able to give the answer of the doubt at that time, but that I assure you that I would give it within this our conference duration. Because I tell you, even my story that image processing, I have actually never ever gone through this code. In my degree part, I have never ever gone through this code. But during my PhD part, when I had been working upon the image problems, because the research topic can come from any part. So during that time, I basically learned the image processing from the different sources, but it was not any one proper course. So whatever I have learned it, that is mainly based upon the application, that where things can be applied instead of any theoretical or any written part. Even that thing actually prompted me that why can't we deliver these things, because uh, in research part, and it is very famous topic, but our during degree part, during our BTech and MTech, many times we do not find the opportunity to read this code. That was the main motivation. Whatever we are covering, that is mainly based upon its application. That's why we introduced it at basic of. Even I tell you that when I am during my MTech, the students, we taught the digital signal processing. There I taught some bits of the image processing. There only I read it, and this is the first time actually when I have been gone through the whole content. And in this journey, my student Suman and Anand, they have really helped me a lot while preparing this content. So now coming to this part, so just we will go through it again, see if you have understood it well. If then we will go through it quickly. If not, then we can imbibe it, that how the things are going. So bit plane slicing, right? Bit plane slicing. See, one thing should be very clear is that in which context we are reading these things. We are reading these things basically in context of the image enhancement. What do you mean by the image enhancement? See, image enhancement basically refers to that the one image is available, one original image is available. How we can see, uh, how we can process that data or how we can process that pixel that its appearance becomes better. Somebody asked me a question that what is the parameter to basically do it. See, right now, see, when we are making the fundamentals, see, parameter things we will introduce it later. That, for example, if I'm transmitting the image from one place, then it is basically that size. Otherwise, it is SNR, signal to noise ratio, etc. Accuracy, that how much accurate, what you are seeing it. But right now, the main thing is the appearance. That because, for example, some image is there, one image is there, I have processed it, how much better it has become now to comprehend or to understand. That is the main thing. So parameter is not clearly defined when we are going through these things. So bit plane slicing, or we can contrast stretching, I think that you would have well understood. So bit plane slicing, when we are saying, see, this is basically the image enhancement technique. So how we are enhancing the image, that we will read it here. So bit plane slicing is a technique to analyze the individual bits in the pixel value where each pixel is represented by a binary number, commonly using 8 bits for grayscale image or 24 bits for color image. The process of, so what we are saying, so we go through this, for example, this is some images there, right? Bit plane. We will go through it. So what we are saying, this is some images there. So what we are saying that we will separate our digital image into its bit plane, right? So, and we will then analyze the each bit plane. So what is, yes, it enhances the images and as well as it is used for the compression. How? Because we can allocate the more bits to important plane, saving space while keeping vital image features intact. So this is the example here, some input images here. This is basically 5 by 5 size is there, 5 by 5 pixel means 25 pixel is there, right? So how do we do it? So first thing, whenever it is there, we we convert into the form of the bit. So for example, this value is there. So what we are able to infer that it is basically 3 bit. 3 bit is there. So we will represent in form of the binary. So it is converted to the binary and then it is represented in this. Thereafter, what we will do, we will do the bit plane extraction. What we'll do in the bit plane extraction, now you see one thing. That this leftmost is basically MSB, most significant bit. This is the middle one and this is the last one. Right? This is the most significant bit and this is the rightmost, this is the least significant bit. So what we are doing here, see, now this is the same 5 by 5 size image which we have seen earlier. But now it is all in basically every pixel intensity is represented in form of the bits, 3 bit, right? So what we are saying, we create the basically bit plane. How do we create it? Bit plane by separate out the bits. How do we separate out? See, first plane we create when we take the most significant bit from the every pixel. 0, 0 here. 0 here, again here is 0. Here you can see 1, it is also 1. Here it is 0, so here it is 0, here it is 1. So what we have done here, how we have created the first plane, we have created the first plane by taking the MSB from the every pixel. Go to the last one. Here it is 0. Here it is 0. Right? In the same way, when we have taken the middle bit we have taken, and it is the 3-bit. So this is the second plane. This is the third plane. So can you tell how many planes are possible? How many bit planes are possible? Maximum bit planes are possible in any image. Are you? Can you guess? 8. Sojan has answered it 8. Any other answer? Saraswati is saying it is 16. Is there any more possibility? For example, here 1, 2, 3. So I repeat my question that whether is there any more plane possible in this image? Is it possible? Combining 2 bits? See, remember one thing, no more any plane is possible, because only when we create a plane, that is only by the single bit. For example, we have taken it, and it will depend upon the total number of bits in a one pixel. For example, if 3 bits are there, then 4 bits for see more accurate. But what we are saying here, see, for example, maximum 3 bits are there, so maximum 3 planes are possible. If somehow our pixel intensity is represented by the 8 bits, then 8 planes are possible. So since we have taken the basically gray level from the 0 to 255, it is so 256 value, it is which can be represented by the 8 bits. So that's why 8 planes are possible, maximum. But in this case, the pixel intensity is represented by the 3 bits only, so maximum 3 planes are possible. Right? So to the next one. Now we come to our normal grayscale image. Whenever we are taking the basically grayscale image, remember by default its level is from 0 to 255. So it is 250. So how many bits will be there in the 256? It will be 8 bits. So how many planes are possible? How many bit planes are possible for one image or one grayscale image? That is also 8. So that you are seeing here. So this is the plane. This is the plane with the LSB, least significant bit. Then it is the second one. Then it is the third one. Then it is the fourth one. Then it is the fifth one. Then it is the sixth one. See, then it is the sixth one. This is the basically the seventh one, and this is the eighth one. Eighth one, which is with the basically the MSB. This is the LSB. Is it? I hope it is clear. So what you can see, what is really important or the very important observation, that with the in the eighth plane with the most significant bit, your figure is much more similar to the original one. How much similar that you can notice here that even see the small number, this A5714, which is basically the code on the dollar, that you can also easily able to observe it here. Even see what you can see, even that number. So details are available at such a level. So this thing is also used for the compression. Because see, instead of basically 8 bits at every pixel, so for example, if my image is basically size of the 5 by 5 means 25, so 25 multiply basically the 8. So 25 multiplied by 8, it is basically 200. And instead of 200 bits, I can transmit it with only the 25 bits. Such a reduction. As we have already seen the problem day before yesterday, that how can the reduction in the size of the bits can really help in compression as well as in the fast communication. I hope see you would able to understand the significance of bit plane slicing. Any question? You can see the another image, another example. The original image is there. See, uh, this is the original image that is basically of the some newspaper. In newspaper, what you can see this clip in. See now you notice it and there's a bit plane 8, which is with the MSB. In the MSB, you can see basically, are you able to read what is this written? Are you able to word? What is this written? This is basically image of a newspaper, possibly. Can you read it? What is written in this and circle? Any guess, any answer if you are able to see? I hope see the image what I am seeing clearly. It would be available in the same resolution at your end after the communication. Are you able to read what is in this circle? Two words are there. Very, very good. So Vivek has interpreted this is the good news, right? So see what you can see here, that very, very small letter is there that you can see here in the bit plane 8, it is visible. In the bit plane 7, it has become difficult. So what we can say, but see here you can say already the 200 bits. Yes, that year, good news. Absolutely. Yes, that is also there. So yes, so what we are saying here, so in the this with only 25 bits, we are able to represent the image in all without any loss, right? The same way you can see the other images, for example, of the cat is here. In cat, it is most significant bit here, then it is the least significant bit. In the same way, for example, this arrow, this plane is there, which is basically landing. There also we can see the image. But remember one basically were simple thumb rule that it is not necessary that we can always apply the bit plane slicing. Because for example, many times you miss the information which is actually required. So it is always depends upon our discretion that whether even see despite after compression, whether can we use it or we can't. See now coming to the part basically histogram processing. So histogram processing, as we already see discussed it clearly. So what did we do basically in the histogram processing? Histogram processing, uh, see histogram will be say the frequency of the pixels as we basically considered it. So on the x-axis, you can see basically the uh, different intensity value. On the y-axis, it is basically the frequency, that how much it is repeated. So Key thing here when we are saying that histograms have a wide application in basically the image brightness. Not only in brightness but also in adjusting the contrast of an image. So what do we do? What does it happen here? So that we will see here. Remember why this thing is followed, because histogram etc. This frequency, it is the easiest thing. Because if somebody gives me an image, for example, image contains the pixel intensity, go to the image. See the work which we can vary, which we want to do or which we can do very easily. There's the number of the counts of the different pixel intensity. So it has so because this is the easiest job, and somebody is asking that how can I use that easiest job into my research or into my any application. So it has been shown here that intensity function is there. In intensity function, it is what has been shown here, that how do we draw the histogram? Here basically, here it's the chain. Intensity actually, which is actually on the x-axis. Here the diagram is it in this way. It is a bit tilted one. This part is the intensity that is on that is basically the we say independent axis, basically the x-axis, and on the y-axis it is basically the this uh, basically 0 to 3 to actually this is between this region. So what it is saying that 0 to 3 is there, 3 to 6 and 6 to 9. We have demarcated this region. So what we are saying that between 0 to 3 the values are, so all the values are basically 0. This is not the histogram, this is only the intensity function. And between 3 to 6, all the values are basically at the 127 level. And between 6 to 9, 6 to 9, if you see here, all the values are white only. White means it is 255. It is a maximum value at the grayscale. So please be clear that this is not the histogram. This is not the histogram, but this is basically the intensity function. But can we draw the histogram? Yes, we can draw the histogram. In any histogram on the x-axis, it will be the intensity. The independent value is basically the gray level intensity. So that has been shown here. That is 0 to 127 to 255. And on the y-axis, it is basically the count, or it is the frequency of that intensity. As we have already discussed it in the last slide, that the histogram of an image like other histogram also shows frequency or the count. Image histogram shows frequency of pixel intensity value. That has been shown here. This is 40, this is 30, this is 30. So this is 0. What we can see here, 0 it is there, here it is 127, here it is 255. How many 255s is there? It is this one. Based on the intensity, we can draw the histogram. Absolutely. On because see, intensity is the independent parameter. When intensity will be given, so on the one part on the x-axis, it is the intensity. On the y-axis, it is the count of that intensity. That how many such intensities are present in an image. See, one quick check whether whether does this on the this left hand image part and the right hand, is it absolutely correct one, or is there any change? This is the proper gray level histogram. Quick question to everyone, those who are seeing it. Whether is it correct one or is there any change? Waiting for your answer. It may be, there may be a, see, that's why I am asking it. See, because one thing is clear that here there is a change. What is the change? That three intensities are there. One is 0, another is 127, another is 255. That is absolutely right. 0, 127, 255. So this part is absolutely fine on the x-axis. On the y-axis, it is basically the 40. This is the 30. This is the 30. So 1, 2, 3, 4. Here 1, 2, 3. Here 1, 2, 3. The correct one? Yes, absolutely. Sumitra responded out correctly. That here, see, it's a bit changes there. It is not written clearly. It is 11. Yes, so this is the correct. So, say no, no, see, intensity, it is matching the intensity because see, intensity function is there. It is 0, 127, 255. That is exactly there. So there is no mismatch of the intensity. What is the mismatch here? That is basically the occurrence of there. That how many total values are there. So here it should be the basically the should be 44. Here it is 33. Here also it is 33. What is the this size of this image? Because here it is 11 rows and it is 10 columns, so it is 110. If you will add up 44 plus 33, it is 77 plus 33, it is 110. So it is absolutely fine. This is the change. Now see, one thing is clear that histogram plotting is very easy to do. But next question arises, what we can do with that part. So that we will see in this slide. So before doing such things, see, even see this is very common thing, very important technique in the research. Whatever you find it simple to do, your main job, how can I apply that simple thing in my research? Because you can do it, you can carry out that task easily. Now you need to ask yourself that how can I correlate it, how this thing is correlated with my research. So now what we want to say that yes, I can easily plot the histogram, but how is it related with the image? That basic question should come in our mind. So when we see this image, what is this? These are basically some nuts are there. So when we plot the histogram, we have plotted the histogram. Plotting the histogram is not a difficult thing. But how is it related with the image? That we want to see. If you see here, see this image is there. So what we observe that when the dark image is there, all histogram is basically located in the left side of almost in the left side. When image is basically my bright one, then my histogram is basically located in the right side. Are you able to observe it? In the low contrast image. See what do you mean by the low contrast? And low contrast is basically, it is not that much dark, but it is almost blurry type image. There what we can observe that it is all the things, whatever you are seeing, low contrast, it is basically the middle part. Are you able to observe this thing? Yes, see, now also realize important one thing, that in the dark image, bright image, remember this pattern has not changed. Remember this same pattern is there. Even this same pattern is there. Almost, yes, the values are there. On the bright image, it has been shifted to the right. Even in the low contrast, it has been shifted to the in the middle part. So see what a beautiful thing is there, that I if I kept my histogram values in the leftmost part, it is the dark image. For the same values, if I take it towards the right, then it becomes the bright image. And for the keep in the middle part, then it becomes the low contrast image. So how you can do it? So one thing very, very clear, that if in the dark image, if I can add up the values in the intensity in such a way that so what do we need to do? We need to basically add up the sum value, so that this part shifted toward the right. So this is what is this thing. So by adding the values and shifting it, I can make my dark image to a bright. I can make my dark image to a low contrast image by adding the in between value. Low contrast, the range of intensity values is small. See, but if you see here, yes, but almost it is same. If dark and bright both are there. See, this is actually with respect to one image only. Whether you have to say whether it is the dark one or the bright one. What we are saying, that if my image is bright, I can make it dark by using this histogram processing, by shifting that count towards the left hand side. Only I need to find out a suitable mathematical function. Important thing here is to see that correlation between the position of the histogram and the your nature of the image. Now you see that in the high contrast image, these are the observations. In high contrast image, see, when we are able to see the minute details of the nuts, that detail in bright image it is bit available, but in high contrast it is very easily visible. One question, what is easy to conclude output in the bright image with a high contrast? Yes. See, if you see, it is best visible in, yes, in high contrast. If you see the image here, which is accurate. See, you can, Saujanya, you can yourself see here. These all the four images here. See, for example, when you go to the market, for example, you are selecting the dry fruit. Somebody asks you, already dry fruits are very expensive. So when you need to select it, and somewhere some basically sign is there, black sign is there, you will discard it, right? That we do it. So for example, somebody say, no, you can purchase these things online. So I am sending you the image, right? For example, you can purchase these things on the Amazon. You don't have the time to go to the shop. So which image is the best one to decide it? To decide the quality of the nut. Can you tell me? High contrast, low contrast, dark, or the bright one? See, if can you answer it? Which image is the one where the customer can decide the best one? High contrast, definitely. Remember, even see if I am a very good nuts. For example, I am sending the almond or the walnut. If I have very good quality, but somehow my image quality is bad, which is visible on the website, nobody is going to purchase in case of the dark and the low contrast image, because people will suspect it that something is wrong. We are not able to decide. Definitely, we need to go to the high contrast. So this is the thing. Not always go to high contrast. We will see it. This is the one. This is basically the essence, that with the position of the histogram, we are able to decide the nature of the image. That leads to the histogram processing, and that becomes the base of the technique. Now you see the another image. Basically, this dark image is there. Initial image is there. So as soon as it is dark, all the basically the pattern of the histogram, it is basically lying in the left hand side. Here see the figure is plotted. In the last case, it was basically the discrete values. Here it is continuous, so you can easily see that there is no change in the pattern, right? Now you see the bright image. Bright image, again it is toward the right hand side, that you can see here. Now you go toward the high contrast image. High contrast, so in high contrast, see here it is the as we decided out that it is the best image. So what is the common here? Is the pattern same of high contrast with the other images, dark and bright, or is it different? Are you able to, which baby image you are able to, which one is better? High contrast. See, now my question is there. See how the histogram pattern in high contrast is different than the histogram pattern in the other images. The pattern means here you see the shape. This is the one. See, this is a peak. Then this mountain is there. Yes, absolutely. Vivek has basically pointed out. Yes, it is the same shape. Shape is same, but it is spread out in between. Absolutely. Right? Here, see, little bit some mountain is there, right? Some mountain peaks are there. Here it is same, here it is same. Here in low contrast, it is bit shrink. But and in the high contrast, it has been basically spread out. That is the thing. But pattern has not changed. Please notice it, pattern has not changed. So now we based upon these observations, then people gave the different techniques. Histogram processing is a general technique. Is the general name of the histogram technique. Now we will move to the specific techniques of the histogram. So what do we do in histogram sliding? We just simply shift a complete histogram rightwards or leftwards. Why do we do? We basically do it to change the either some image, to change the darkness and the brightness. For example, this is there. This image of Einstein, see, you can easily able to see it. And then this one, this is basically the bright one. What has happened? It has shifted. See, this pattern has shifted towards the right. So how does it happen? Again, here this old image, this new image is there. Here you are seeing it. It has been shifted. So what we have done? There, basically, you have basically added up to here. This count is there, so you have basically changed the. We need to find out the mathematical function. But what we are aware that this is very easy to make the image from the very easy to increase the brightness. Even see, it is the same thing if you would have noticed in the earlier black and white TV. They have following the thing. Now we move to the another technique, histogram stretching. What do you mean the histogram stretching? Histogram stretching is basically used where it was used. It was used basically when we had been making the high contrast image. What we have done here, that expands the range of the intensity levels in an image so that it expands the full intensity range. Remember, it is from here, but now it has been expanded to the board. How do we do it? A very important part, because when we apply it on our image, we need to write a mathematical function. We need to write exact formula. So remember, if you recall the word S is basically the pixel intensity or the output image. R is basically the intensity of the original image. S is of the output image. So what you are doing here, this transformation. So what you are doing, S equal to this one, 255 R max minus R min, R minus R min, this formula. So what is this R max? R max is the maximum value of the intensity in that image. What is R min? R min is basically the minimum value of that intensity in that image. And what is R? R is basically the intensity of that current pixel. What is this? This is basically the transformation function. That's we have done it here. Histogram, this is basically initially histogram is here, fxy. So what we have done here, remember, please note it here that we have stressed out. That's why it has become high contrast. Why we are stretching out? Because it leads to high contrast, and high contrast view is much more better. Its appearance is much more better than the other images. Again, he has shown it that dxy, it is basically 255 multiplied by R max minus R min upon R minus R min. Shown here, this formula. So this has been shown here. This original value was there 84. Remember, since 84 is the minimum, so 84 minus 84, it is 0. It has come here. So in this way, it has plotted all the values. What happens? Already we have seen the impact of the histogram stretching, which basically makes the image high contrast. Again, you can see basically one of the scene near the seashore. So the one person who is climbing up on the rock, see, here see, it is very, very clearly visible. Here you can see that how many things. So here you can see what is basically the histogram pattern on the left hand side. It is between the in middle, and here it is the spread out. Can you tell me whether this image is the dark one, the bright one, or the contrast one, low contrast? See whether this image is the dark or bright or low contrast. Need to use a natural image processing. Is this high contrast here, this one? No contrast. See if yes, see if you see this image, you remember again, I hope see you have missed one thing. What we are going to do. See, notice this thing. See this diagram here. This is basically dark one. This is the bright one. This is the low contrast where the pattern is basically the in between, right? So in a same way, what you can observe here is this is the thing that it is the in between actually. See, dark one is where you are hardly able to observe any detail. That you can see here. Almost this is the dark one. Very hard to note the detail. This is another dark one. Low contrast, see, definitely it is not that dark and it is not that bright. So, what is the important thing? Important thing is the in between locations. See, how am I able to find out? I am able to find out because the values of the histogram are in the at the middle. This thing will always hold. I hope it would be clear to you. So whenever image is there in the low contrast mode, I have simple formula. I have one very good technique that I will make it high contrast. How will make it high contrast? I will spread out. I will do the histogram stretching. That's why we very quickly do the histogram stretching. So that's why histogram is stretched in this. Not only see histogram stretching, for example, see in the online, see today actually it's a time of basically the distant health center. For example, in Rajasthan, in Jodh, Jodhpur, as well as Abu roads, it is distant actually. Some medical centers are there which are connected with the AIMS Jodhpur because those rural people can't go to. So what do they do? Whatever see the reports are there of those people, they send it. They share that image. For example, I share that image of basically the chest X-ray. This is very difficult to remember all the detail. Any doctors, if somebody they have to detect whether that person is pneumonia or not from the chest X-ray, it is very difficult. What is this image here? It is whether it is the dark one or it is the not definitely brighter, dark one or the low contrast. It is low contrast. Again, see that is the see beauty. See, once you are very clear with the pattern, you can very quickly find out that it is basically the low contrast. So when the low contrast, I can easily make it using the histogram stretching. I need to apply that algorithm and things will be fine. And here you see the image is much more visible about the chest. So, but see when somebody pointed out that histogram, one thing is clear that the high contrast images are very good to observe. But histogram stretching is not always good. Where it is not good, that we will see in this example. See, this is basically some cultural, some sign board is there. What you can see here, that this is again the low contrast image. But in this low contrast image, the values are basically starting from the zero. See, here this zero count is there. Unlike the earlier case, see here no more zero count is there. Complete histogram or the complete pattern was located in the middle part only. That was located in this middle part only. But when you come to this part, you can adjust the pixel just a minute. But here you see it is not located in the total in the middle. Here this part is also there. This. Remember, when this type of cases are there, your histogram stretching leads to this image, and that is not a very good option. It has a limitation. Then what do we need to do? then you can apply the another technique that is basically called the histogram equalization. When do you need to apply histogram equalization? When your value or when the histogram pattern contains when it is not not located in any particular region. It is already spread out. If it is already spread out, especially towards the zero, then it becomes difficult to get the good image by histogram stretching. So, so what is the alternative? We do basically histogram equalization. What do we do in histogram equalization? In histogram equalization, it has been spread out. In stretching also, it has been spread out, but it has even see you note another thing that it has been spread out totally. So basic question. So what do we do? That the gray values is uniformly distributed in 0 to 1 with an dynamic range of pixels. Is there any denoising? See, denoising actually will come later. Here actually we are enhancing the image, right? So how do we do the histogram equalization? Do the histogram equalization. For example, some original images there. See, why you people would be thinking, see, why do we start with basically the such a small value where maximum value is 7? See, we take it so that uh, we can understand the basic principle. Can later on be then transferred to a 8-bit values also. But initially 3-bit values are more easy to. No, they are 8-bit. They are only we are 8-bit. We have taken all the 7 gray levels. What it is saying, it is 0, 1, 2, 3, 4, 5, 6, 7. So how many counts are there? For 3 value, it is 6, 1, 2. This is 1, 2, 3, 4, 5, 6. At the 4 value, this is basically 14. This is the 5, 5 value 5, 6 value 0, and this is there. So this is an histogram is there. So how do we apply the histogram equalization here? When we want to apply the histogram equalization, see what do we do when we do the gray level? First we write all the gray levels, then we write the number of pixels, then we write the PDF. What I meant before, it is based on number of pixels. Can you? Is there any denoising? See, right now, see, we are not focusing denoising. See, how do you define the noise actually? Then only the denoising concept comes in observation. What I mean before, it is based on number of pixels. See, no, but number of pixel can never ever be the base of the noise. Pixel, it is basically a part of the original image only. Adjust the pixel. And you know, issue. So what we are saying here, you find out basically the number of pixels we have find out do in histogram, these two columns are there. But from these two columns, we basically calculate the PDF, probability distribution function. Probability distribution function, what we are doing, we divide it by the total number of counts. When we are dividing by the total number of counts, so what happen, we will get all the values between 0 to 1. We will get basically the percentage. Probability distribution function, right? So that has been shown here. So it is 0.24, 0.56, and then it is 0.2. Remember, it will always add up to 1, probability distribution function. Then what we are doing? Then from it, we are creating the cumulative distribution function. What do we mean the cumulative? In cumulative, basically, they are showing it is, see what they are showing. See, it is 0, 0, then it will move where 0, it will add up. The sign is there of addition, 0 plus 0, but it is again 0. Again, it is 0 plus 0. What will it come here? Again, it is 0. 0 plus 0.24. Here it is plus 0 plus 0.24. So then it will come 0.24 here. So in this way, you will create all the other values. That's it. Now what you will do, you will basically you will this SK value, we will basically multiply by the maximum value of the gray level. Maximum gray level. What is the maximum gray level? Gray level is basically 7 only. Total 8 gray levels are there. So when we multiply it by 7, we will get these values. 7 into 0.24, etc. So thereafter, so what we are getting, so now after multiplying, we'll get some value 1.6 and 5.6. So what is the rule here? So we will then replace it by the complete number, the 1.68, which is the nearby number is basically 2, and 5.6, it is basically the 6, and then by 7, it is already it is 7, so no changes in that. So what we are saying here, so this value, so in the new image, when you will take it, so that these, yes, whatever these values are there. So for example, earlier 6, 14, 5 was there, 6, 14, 5. After equalization, see this 4, what you are seeing, this 4 here, 4 is replaced by the 6. 5, wherever 5 is there, it is replaced by the 7. Wherever 6 is there, it is replaced by the 7. Wherever 7 is there, 7 is replaced by the 7. So same in input image, we will replace it 4 by the 6, 5 by the 7, 6. So that way we have done it. So then another histogram pattern will come out for the new one. And but this is the, so what do we need to do? We have basically created the new image, and then you can see that output image that it is much more better than the earlier. Any, you can see the impact of original histogram, image and its histogram. So this is the one here. So again, what you can see here, that this is basically the dark image where your all the pixel values, intensity values lie on towards the left side, and see the then what we are doing, then we are applying basically the histogram equalization. When we have applied the histogram equalization, this is, you can see it. The important thing in the histogram equalization, see, it is a totally spread out, even see more than the stretching point. There you can see the resultant image after the histogram equalization process. In another case of the histogram, see, but remember there is also a problem. For example, it has also some limitation. What limitation are there? That histogram equalization may not always produce desirable results, particularly if the given histogram is very narrow. For example, see, this histogram is there, but it is actually narrow. So this histogram is there, that is basically narrow, and that's why here when you will use the histogram equalization, it will not give the what And lead to it can produce false edges and regions. It can increase the image graininess and patchiness. So how does it look like? When I applied the histogram equalization, it has resulted into this one. Actually, so that is not solved our problem. Is it clear? So remember, techniques, some techniques work better, some techniques work at another place better. See, today, if you really see the image processing, for example, CCTV cameras are there. And CCTV cameras, you even see it has become the basis for criminal investigation. So there you see the different type of cases. For example, some scene has been recorded in the evening, something has been recorded in the evening, or somehow we need to take the decision. Then these techniques become very, very helpful. So this is the limitation of the histogram equalize. Here also when we have applied the histogram equalization, this is the new image, this is the old one. There, what you can see, it has been spread out. So there are some problems are there. For example, you another take the example where this is basically the uh, remote sensing image, not remote sensing. It is basically sent by the some space basically on possibly on the moon actually, right? Some moon surface is there. So how does it look basically? Remember, if you do the histogram equalization, the resultant image is this one. So why this problem is there? This problem is again here because can you tell why this problem is coming? Why it has not lead to the good result? Are you able to point out peak intensity? Peak intensity, it was there. See, never ever we are bothered about peak intensity. Actually, no, no. See, actually means the that's why we need to do the actually the thing. This is the actual image. See, if you really see the thing, see, it is located in a very, very small region, in very, very small, thin region. When your region is very, very thin, then it really becomes very difficult that when you will apply the histogram equalization, it will not solve the problem. It should have the some width. Really want to work well the histogram equalization, it should work. That's why this problem is coming. Can you elaborate, Saujanya? So here, see, even when I have this low contrast image, when I have done it, equalization, I am not able to get the actual, not able to get the detail, what I want to find out. So here we take a break to find out see, what can be the way when histogram equalization has also failed. We'll meet, see, right, just after a 5 minutes, around 5 minutes break. So, so I hope you would have find out the answer. So is there any technique apart from the histogram equalization which can work well? Any guess? So if you recall, we have already gone through these slides yesterday. That is the only basis where you can know that basically it is the adaptive histogram equalization. What do we do in the adaptive histogram equalization? In adaptive histogram equalization, for example, this image is there. When in histogram equalization, you are applying the C processing on the complete image. But in adaptive histogram equalization, you basically divide the image into the portion. This is the first one, this is the second one, third one, this is the fourth one. There we have divided, and now see what we do, that contrast is improved locally. The very important word, this locally. In image, see, whenever you will see the techniques, two type of techniques are there. Even you would have observed in the yesterday's lecture of the Dr. Vivekananda that one techniques work at the local level, another technique works at global level. So local requires the neighborhood part, right? The neighborhood information becomes more important. But in the global part, see, apart from the neighborhood, many other things play an important role. Seat, we would keep in our mind that whenever we are applying the techniques, image processing technique, that where the work has been going upon, whether it is the local or at the global, and how it is going across the global, how the changes are come at global level. So in a step, basically, we divide the image into the small tiles blocks. Basically, here it is shown 4, it can be 4, 8, etc. Again, depending upon our objective. Perform histogram equalization in each tile. Now, see, when we will apply the adaptive histogram equalization to our unresolved problem earlier, when we will, this is a low contrast image and we will apply the histogram equalization. Now this image is bit clear. See, what is important that we are able to see the many spots are there. Even we are able to count these spots. This is 1, 2, 3, 4, 5, 6. One big spot is there which is surrounded by this thing. That information was missing totally in the first original image. This is basically the beauty of the adaptive equalization. I hope see it would be clear to you. Another part, what happens if, but there are some problems in adaptive histogram equalization. What are the problems? That it can over amplify noise in low contrast areas. See, for example, this image is there. See, for example, someone's study room is there, right? Person is studying here, some lamp, etc. This is there. Some board is there. But as soon as we have applied the adaptive histogram equalization, see what has happened that this image, this thing has become a bit clear, but this has become too much bright. The detail which I was here of this sculpture, here it is, I am not able to observe the detail which was visible in that sculpture in this the originally. So small tiles can cause excessive contrast and produce unnatural results. The image can look too sharp or too bright, for example, in that. You can see that is the actual scenario when you take the bigger images, right? Different parts are there. When each tile is processed independently, differences between tiles may cause visible block boundary. Suddenly intensity jump. You can see here, see that the suddenly intensity jumps with block boundaries are there. That is showing. So here again adaptive histogram equalization is not a complete answer. So what is the option? Option is basically the clip limited adaptive histogram equalization. What do you mean by the clip limited? Clip limited means basically when we draw the histogram, see what do? We basically clip the peak. Clip the peak means basically see what you are seeing here. See, you are basically clip it and you have put it at the bottom. And this is basically the clipped histogram. So what we are, and this is very popular basically technique which is used in the biomedical image, even for example for the MRI and the CT scan, etc. So what do we call it in the between? It is Clay limited adaptive histogram. So Clay solves problem of impurity maximization by clipping the extra value. Clipping means we are basically clipping it and we are putting it. See, we are not discarding it totally. We are put it. If any histogram bin is above the specified contrast limit, those pixels are clipped and distributed uniformly to other bins before apply. We will apply the histogram equalization, but later. This is the one. Now we take this example. Now we see the best way to see the new improved technique that when you where your original technique has failed, then you apply. There you can see that the original image is there and clay output is there. So now you can see that sculpture and all the information is bit good available. The original image it is there. Any question? Any question in this clay part? No. So how now one thing is clear that clay is very important. So how do we apply? So what we are seeing here in this example, again we have, okay, thank you. I hope. So what we are saying, how do we apply it? So we first basically plot basically all the this all the levels, gray levels. Then what do we do? Then what do we do? For example, 3 bits are there, so 7 levels are there. So how many values are there? This is basically on the y-axis. It is basically the count. It is 40, 50, 70, 128, 136, 60, 118. Right? This is basically the count. So where will I apply the clip here? Can you infer? Can you guess? Where should we apply the clip? Clip means basically cutting the sum part. Any guess or any inference? If you see here, these 60, see, but 60 okay. If I apply 60, but 60 is already very short one. Or I rephrase my question that which uh, which level value will be clipped? The 4 and 5, absolutely. Absolutely. See, dividing an image into smaller regions, that is basically the adaptive. That was clear. As pointed out very quickly, it is the 4 and 5, they will be clipped. That we will see in the next slide. Yes, this is there. So that we have clipped it. And so what happens is, so this we have clipped here at this level. So we have clipped at 120 level. Remember, we don't want to clip at many level. It should be minimum one. So then what do we do? So we have clipped at 120. So extra value 128 minus 120, it is 8. 136 minus 120, it is 16 and it is 24. So then I say they have high contrast, or we can say yes, they have basically the high, definitely they are number of these pixels are very high. Middle portion is very high. So what do we do with this 24 value? If you recall from the earlier diagram, we will put it. You put it at the bottom. Where we will put it? We will put it here. See, this is 24. So where we have to put it so that the other can also come up. So other, how many other levels are there? Apart from this thing, 1, 2, total 8 levels are there. 8 minus 2, 6. 6, 24 divided by 6 equal to 4. So we will add up the 4 value. So 4 will become 0 will become 4. 40 will become 44. 50 will become 54. 70 will become 74. And in this. Is it understood? 4 and 5 high contrast, so which is equalization. We come to it, see. So what we are seeing here, so this is 120, 120. Now what do we see here? Because it will add up at the 118 and it will add up to 122. Now it is this 122, it will be clipped because 120 is basically our threshold level. When this threshold level is there, so two values in the addition. So two values should be divided between the how many values? Other 5 values. Because 2 are already above it. 1, 2, 3, 4, 5. So 2 divided by 5 is basically how much? 2 divided by 2 divided by 5 is basically the 0.4. This 0.4 can't add up because these are the complete values. So what we will say, 2 you have to directly add up. So where you will add up the 2, which is in basically the minimum value. It will say the 0.4 actually, right? So what we are showing here, this is 0.4, and when this 0.4 will, it can't be add up in this case. Just a minute. So here you can see here, so 4 when it is add up in the 2, it has become basically the 6. This is the new level of the value. So is it understood? So see, this way we have done it. This is basically the new level of the play, and again then we can redraw the image in this. So this is one of the most important techniques used by the biomedical researcher. Now another technique is there in the histogram matching. In histogram matching, basically what do you do? See, for example, some good pattern is there in one image. You want then using the histogram matching, you want to bring that pattern in the original image. What has been, so how do we do the histogram matching? Histogram matching, see, for example, the gray level, we take up the example that how do we implement it. For example, gray levels are given between 0 to 7. Then the hair count is given. Basically, the total count is given. This is 790, 23. So total N is this one. We calculate the PDF. It is exactly the same way we have done it earlier. Then we calculate the CDF, cumulative distribution function. This is 0.19, 0.25, 0.44, 0.44 plus 0.21. It is 0.65, 0.65 plus 0.81. So there we have add up. Finally, the final value will be 1 only. SK into 7, so the maximum gray level, maximum value of gray level, we have multiplied it and we are round off. When we are rounding out, so what this is given, that round off value is 135, so this one. So what does this infer? So we can replace, we will replace this our gray level 1 by the 3, 2 by the 5, 3 by the 6, etc. What will be the new count of this one? So what will be the new histogram? New histogram, again you can see now, since it has become the 6, 3 has also become the 6, 4 has also become the 6. So now the total count will be 656 plus 329, that is 985, and this is the this one. So we want to see the pattern. We want to see the pattern of the histogram, see how the pattern of histogram has moved or has changed in the histogram matching. So that we can see here. So earlier it was basically the very well distributed histogram, but after the histogram matching, it has shifted towards in a very particular region that you can see here. So now you, for example, so this is the one. So for example, you want to do it for the image, this image. Now I want to equalize the histogram of B image where the 7 levels are given and this counts are given. Again, we will do the thing PDF, probability distribution function, then cumulative distribution function, and then we have calculated this round off function. Please be clear that we want to make the image B like the image A. We have not done any processing in the image A till this part. Only we have seen it the new histogram. But how will it be done? That is still to come out. So this is a round off figure is this one, right? So now how will it be done? So that you will see here, you do the mapping. This is the actual technique. This is the actual core of the technique. That first and the last columns of histogram. You will take it gray. See, first and last histograms you see of gray level and round off level. Gray level and round off level that we have taken. It was basically the initial gray level. It has changed to the this level. It is a new level. 0 will become 0. 1 will are considered as 0. 2 as 0. 3 as 0. Other thing. 7 as 7. Then you take the, where do you need to map? You need to map basically your target image to the original image, B to the A. Last two columns you need to take of the histogram A, the round off value and the new number count. 790, 23, 850, 985, 448. Again, this is the last column. This is basically the first column. Last two column actually we have taken. This one round off value and this. But why we are doing it? We are doing it, see, because we want to find out the histogram, new histogram. How will you find out the new histogram? When we will able to map the gray level to the frequency, to the new frequency. So what is the new frequency? See, this 3 value towards the 1 and this 1 towards the 1 and 1 towards the 790. So this 3 value will contain 790. This 4 value contain the 1023. 4 to 3, that is directly mapping, and then 3 to 3. This 5 to 5 here, 6 to 6, then 7 to 7. See what a wonderful technique you see. The people have applied it there and they are able to do at the image level that whatever portion you want to learn out or implement from the original image. The original image was this one, or which was basically the ideal image where I want to learn. And who want to learn this image? The image. And see, this is a new histogram, and then you can redraw it. What is a simple technique, but very, very effective technique. But see, I really, when I'd been going through these techniques, I had one question in mind. See how people are able to produce these techniques. Whoever person was a developer. Again, see, it's bit your observation. Bit sit silently and see the thing. Remember, research will never ever come when you are running towards. You sit down simply, you see the things, how beautifully things are happening, what interesting combinations occur, and then you begin to realize the thing, many, many important thing. That is actually the research. So see, those people, see, for teaching is one part, but those people who are doing the research sit comfortably, silently, and enjoy the thing. Enjoy those interesting patterns. Write it in your copy, in your sheet copy, and then leave out for some time. Then again see those patterns, what is coming there. Common suggestions, you will really find out such beautiful things. What is a wonderful thing? From histogram itself, where simply we are uh, counting the things, what important patterns have emerged. This is basically the histogram. So this is basically the histogram of the input image. What you can see that 0 to 7 level are there. This is 790. This part is there. Then we specified the histogram. Which is this histogram? This histogram is basically the come out from this one only. Which one? This is my, which I want to, this is the ideal one. Here I want to learn it, 1230. This is a specified histogram. And this is the output image. It has learned. See, this histogram has changed to this one, and this has become whatever pattern it wants to learn from this image, it has learned into this image. This is the idea. So like this here is the so transformation कहाँ पे आया? The transformation has come from in this image. Earlier this image and this. Any questions? What an interesting result. Any question which is clear in for any part. Then is there, so we move forward. But see, histogram has also the limitation. Where see histogram has a limitation, can somebody tell? Remember, two things are very important in life. One is basically observation, another is criticism. Criticism is very, very important part for the development. So can you criticize histogram that where any type of technique of histogram will not work? Now you have observed many things. It's a time to criticize. Any idea, any guess, definitely. But once you begin to think about it, at least you extend your thinking. That's why I usually emphasize upon asking the question so that you may not be exactly correct, but you begin to apply your mind. You begin to extend the mind. Answer is in front of you. Any answer, even see it applied on entire image, but entire image is definitely required. So you can apply on the local level also. That is not a problem. It is pixels. If pixels, can it really be the problem? See, good resolution, no, it is not really necessary. See, resolution is again in your hand. For example, I can take the different device, I can increase the resolution, or see, definitely some images there which is of limited resolution. I can't say to another person that please give me the better resolution image. See, we are image processing engineer. What we are thinking from the engineering perspective. Somebody is giving the image, we can't say pre-processing histogram is basically the part of the pre-processing. Whatever these techniques we are doing, these are all part of the pre-processing. To be real times we do the thing, these all this is the part of the pre-process. See, I give you the one hint. For example, mapping and changing values of pixels are not see, yes, they are time taking, but definitely it's a very not difficult one. Yes, it is time taking, but we are able to do it. See, for example, we say two child are born at the same time. Then it is a twins, right? Two twins are there. One has become very good. Both have exactly birth at the same time. One has become very, very good person. Another not that good, or he is considered as bad person. So what is basically the problem? What is the cause of it? Two twins are there, exactly same parents, etc. But one has resulted into a very successful person, another not that successful. If you see any guess here, we have converted it into a human problem. So as a human, see, we are very, very good to interpret the situations around us. The way of thinking and learning. One word answer, what I'm seeing. If you last guess, if somebody can guess, see the answer lies in basically the neighborhood. For example, when I am talking about the twins, if one twins, for example, joins the good company, he has good friends, he or she has a good friends, then despite with the equal capability, equal mental caliber, see, his life will change because when he will take the decision, he is surrounded by the good set of friends. The good set of friends with good habit, who are disciplined, who are hardworking, bit sensitive, they are empathetic. On the other side, another twin, that person has really, she or he has a set of friends who are basically always competitive, insecure, hostile, very, very angerful. So remember, it's basically answer lies in the neighborhood. So what do you see? If you see this image, if you will draw the histogram of these two images of this zebra and the dog, see what you will see. You will see clearly the same histogram of both these things, right? So when you will see both these things, that both histogram is same, but where the difference is there. So by the histogram, see, I can't differentiate. This animal, this looking like zebra, and this is dog. But where I can differentiate, we can differentiate. See, in the neighborhood, see, this black pattern is there. Here, this neighborhood is different. If I take the patch, it is different. What happens? See, in histogram, this neighborhood part is not taken into care. What we are saying, both zebras and this breed Dalmatians have black and white pixels in similar number. Same histogram. Difference between the two is the characteristic appearance of a small group of pixels rather than the individual pixels. See, here you see this pattern is totally bit different in both of these. So this neighborhood actually is ignored in the histogram, which becomes very important in the image processing. So that's why the another technique became popular. That is basically the spatial filtering. Spatial filtering. So as we have already discussed it, that it aims to take care of the neighborhood. So our main emphasis when we will go through this technique, that how does it take care of the neighborhood? What is its so when we have the keen observation that how this is taken care of. So it is taken care of by using the mask. What is mask? Mask is usually considered to be added in size so that it has a specific center pixel. This mask is moved on the image such that center of the mask traverses all image pixels. Remember, the keyword in the spatial filtering is the mask. What does mask do? Mask takes care of the neighborhood. For example, if I want to know any person, for example, it is the Saujanya Jyoti. See, I can't understand them by interacting them individually. I also want to know that in which group they are living. If you will allow me the set of friends, 10 set of friends, which are the best friends, I can very well understand that which type of person is he or by seeing their friend. So that is basically the role of neighborhood. So spatial filter consists of neighborhood and a predefined operation. So that we will explore. So how does it work? We are as an engineer, we are very much interested see how the mathematics will be laid down so that we can process that thing. Right? Understanding observation is one thing. Applying the mathematics, developing the mathematics is the next thing. If you are able to do it, then our job is done. Our research is done. So that you are seeing it here, basically the image origin is, so this is basically some image is there, pixels is there. See what is basically mass? Mass you can see here. See, this is mass. This is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 by 3 mass. Right. As we discussed it, mask is added in size, it is specific center pixel. What is important that it has a specific center pixel. What is mean by this specific center pixel? It is this one. It has center. It is all surrounded by this one. So it is all. It will always be 3 by 3, or it will always be 5 by 5, 7 by 7 in this way, because so that it has a specific center. Now, how do we represent it? So center one we coordinate at W00. The above one, basically it is -10, below one it is 10. On the right hand side it is 1, etc. So this is the nomenclature. This is fxy, this is x minus 1y, this is x plus 1y. Again, see, some people may be thinking that how can we take x minus 1? See, you can take any convention, but see, this convention has been followed. Right. This convention has been followed that they have upper value they have considered x minus. Only it is the representation of this spatial location. Above line x1 it is x minus 1. Below line it is x plus 1. Right hand side it is same y plus 1. On the left hand side it is y minus. Now see on there are two type of spatial filter. One is basically the linear spatial filter. Another is basically the non-linear spatial filter. Remember, whatever things, whatever basically, even yesterday we discussed it, whatever today we has detection or whatever task you believe it, up people use a filter, different type of filter. So to start with, in the spatial filter, it is basically the mean filter. It is the mean filter. It is basically the Gaussian. It is the sober. We will read it into the detail later. Yesterday, somebody asked a question also, what is Sobel effect? We will go into the detail. But right now, see, just we are discussing at the upper level that one is histogram and one another is filtering, spatial filtering. Filtering basically which focuses upon the neighborhood. And how does it take care of the neighborhood? That we are seeing here. Non-linear spatial filter, that is median, that is max-min, that is bilateral, many are there. So that satisfies the additivity and the homogeneity. So mean filter is simply basically. So what do you mean the mean filter? We take the examples. So first thing, see the simplest filter are basically these mean filter. What do we do here? Then it is an average. Whatever you value, you average that pixel value and surrounding value. We will see it that how do we do it in the next slide. What does happen? See, whenever you are applying any operation in the image, the second question your mind should come that what will be the impact? Histogram matching here. See, we are doing basically histogram matching, histogram equalization. What is actually happening at the image level? So that is the main thing. Mathematics, doing mathematics is one part, but how is it impacting the thing? So averaging part is basically reduce the details of the image. When all coefficients are equal. Another is basically weighted averaging filter. In this, basically pixels are multiplied by different coefficients, center. So what we are saying, see, for example, we want to give the more weightage to some neighborhood. You don't want to give the equal weightage, then you basically use the weighted averaging filter. So here two things will become very important, this correlation and this convolution. In correlation, basically, Correlation is basically used in basically the pattern matching. And convolution is the base of the filter. Wherever correlation is not used, correlation is used in very, very limited sense, but wherever correlation is not used, it is convolution. This is the base of basically the convolutional neural network. If you are aware, this deep learning mechanism, these machine learning mechanisms, these are basically mainly has been developed for the images only. Such as the big contribution from this image processing to a deep learning artificial intelligence, because convolution was a much more earlier concept. Convolution and neural network, it has been applied these days. So here we conclude it because these are very important topics. So I don't want to go through very quickly. We will have the time if we have any question. Any question? Weather related. Okay, so thank you. So we will meet at 3 o'clock with Dr. Himanshu. He's from IIT Bhubaneswar. He was basically well meet there. Thank you. Even see if you have any question at any time, you can email me also. There is no problem when we are discussing that. Thank you.